This is the ELEC 1510 Logic Design Lecture 3, Video 3 on lots and lots of types of logic gates corresponding to textbook section 2.8. I'm going to start off by reviewing some of the gates that we've already talked about. The most basic type of gate is the NOT gate. This one isn't really much of a function even. It's just got an input x and then the output. I've written here z, which is going to be equal to x prime, is just the opposite of x. So whenever the input to this gate is a 0, the output is a 1. Whenever the input is a 1, the output is a 0. It takes the prime of the variable, or negates, or takes the opposite of whatever the state is of the input. OR gates and AND gates we've already discussed as well, so you've probably seen these truth tables a couple of times already. The equation for an OR gate, or one potential equation, is z equals x or y. If you have inputs x and y with the following states, these are all possible combinations of states that the input can take, then the output is going to be a 1 whenever one or more of the inputs is a 1. So if I plugged in the following variables to that gate, it would realize this function. The AND gate completes the AND function. So in this case, z equals x and y. For all possible input combinations for the input variables, the output will be a 1 only when both of the inputs are 1. So the gate set up in the following way: x, y, and z at the output realizes this function. Two additional functions that we're going to talk about are the NOR gate, which means not or, and not and, or NAND. What these mean is that the NOR gate takes the complement of the OR function and the NAND gate takes the complement of the AND function. So if we have two input variables x and y for NOR, the OR function is a 1 whenever one or both of the input variables is a 1, so we get 3 1s for x or y, and then the output z is the complement of x or y, which is 1, 0, 0, 0. Which means in this case it's only a 1 if both of the inputs are 0. So the NOR gate is going to realize this function and give us a 1 at the output only when both of the inputs are 0. The NAND gate looks like this and takes the complement of the AND function. So for input variables x and y with all possible states written there, the AND of those two variables, x, y, is only a 1 whenever both of the input variables are a 1. So then the complement of x, y, or z in this case, which z is x, y prime, is going to be a 1 whenever x and y is 0, which means we get 3 1s at the output, basically whenever one or more of the input variables is a 0. So the NAND gate set up this way realizes this function and produces a 1 at the output whenever one or more of the input variables is a 0. The last gate that I'm going to talk about is the XOR gate. This means exclusive OR. The XOR gate is kind of a weird one that's constructed out of other smaller gates, essentially. The XOR gate has a more complicated function associated with it. It's actually, oops, now I have to erase that. Z equals xy prime plus x prime y. And we write that using this fancy symbol, a plus with a circle around it, to denote XOR. And what the XOR gate does, this function, produces a 1 at the output if only one of the input variables is a 1. If neither of them is a 1, we get a 0, and if both of them is a 1, we get a 0. So the XOR gate, set up in the following way, realizes this function. And so the XOR gate is essentially just an OR gate with an extra line at the concave input. So that's how you draw an XOR gate.